Hello everyone and welcome. Today we're going to break down a really key topic for your WAEC, JAMB and NECO physics exams, the whole world of vibrations in springs and pipes. This stuff is super important, so let's get you ready to ace it. So, what do a smooth car ride and a flute have in common? Sounds a bit like a riddle, doesn't it? Well, the answer is pure physics. They both rely on the exact same principles of vibration and something we call simple harmonic motion. Just stick with me, and by the end of this explainer, you'll see that connection crystal clear. So here's our game plan. We're going to start with some real-world examples to get a feel for it. Then we'll dive into the physics of springs, and after that, the sound of pipes. And you know what the best part is? We're going to use all that new knowledge to solve actual past exam questions. All right, let's kick things off with section 1, vibrations in your world. Before we get lost in all the numbers and formulas, let's just connect this to things you see every day. Why does any of this matter beyond just getting a good grade on an exam? Well, from the music you hear coming out of a flute, to how a car's shock absorbers give you a smooth ride, these principles are literally everywhere. And for your exams, this is a huge topic. It connects ideas from waves, sound, and mechanics. So really getting a grip on it is a massive advantage. Okay, let's get into the core physics now. Starting with springs. We're going to look at that classic back and forth motion. The one you see when a weight just bobs up and down on a spring. The really big idea here is something called simple harmonic motion, or just SHM for short. Just picture a kid on a swing, right? As they swing away from the bottom, gravity is always trying to pull them back to that center resting point. And that right there is the heart of SHM. It's just an oscillation around the central point, driven by a force that always wants to pull it back to the middle. And this entire motion is governed by a really simple but incredibly powerful equation, Hooke's law. F is that restoring force, K is the spring stiffness, we call that the spring constant, and X is just how far you stretched or compressed the spring. Now, that little minor sign, don't ignore it. It's super important because it tells us the force is always pulling in the opposite direction of the displacement. Okay, let's see this in action with a typical problem. Have a look at this question on the screen. We have a 0.5 kilogram mass on a spring with a stiffness of 200 newtons per meter. We pull it back 0.1 meters and then we just let it go. So the question is, what's its period and what's its maximum velocity? So how do we tackle this? First up, we're going to calculate the period. That's just the time it takes for one complete up and down swing. We plug our mass and our spring constant right into that first formula and out pops about 0.314 seconds. Easy enough. Next, we want its fastest speed, which always happens right as it zips through the middle. Using that second formula, we plug in our values and we find the maximum velocity is 2 meters per second. Great. So we've handled springs. Now let's totally switch gears from solid objects to columns of air. We're moving into the physics behind how instruments like flutes and clarinets actually make the beautiful sounds they do. You see, unlike a spring, you can't actually see the air in a pipe vibrate. Instead, it forms something we call stationary or standing waves. This happens when sound waves travel down the pipe, bounce off the end, and then interfere with the new waves coming in. This whole process creates spots of high and low pressure that resonate to produce a specific clear tone. Now, this is where it gets really cool. Take a look at this comparison between pipes that are closed at one end, like a clarinet, and those open at both ends, like a flute. Notice the formulas for their main frequency are different, but the really crucial part is harmonics. A closed pipe can only produce odd harmonics, the first, third, fifth, and so on. Why? Well, think about it. The closed end has to be a point of zero vibration, while the open end is where the vibration is wildest. This physical constraint means only certain wavelengths, the odd-numbered ones, can actually fit perfectly inside.
This is what gives these instruments their unique, rich sound. Alright, this is the moment of truth. Theory is one thing, but acing your exam, that's the real goal. Let's apply everything we've just learned and tackle some actual past questions from WAEC, JAMB, and NECO. First up, let's look at this WAEC question from 2019. We have an object that weighs 120 newtons and is vibrating with a period of 4 seconds. Our job is to calculate the spring constant K. Now, before I show you the solution, just take a moment and think. What's the very first thing you need to do here? Okay, here we go. The very first step, and this is the classic trip-up spot for so many students, is to convert that given weight into mass using W equals mg. Once we have the mass as 12 kilograms, the rest is pretty straightforward. We take our period formula, rearrange it to solve for K, plug in all the numbers, and we get our answer, about 29.63 newtons per meter. So listen up. This is the big takeaway here. Always, and I mean always, double check if the question gives you mass or if it gives you weight. It's such a simple detail, but it's designed to catch you out. Don't fall for it. Next, we've got a conceptual one from JAMB. So, imagine a closed pipe. It resonates at its lowest possible frequency, which we'll call F1. Then the very next frequency that makes it resonate is F2. The question is, how can we write an expression for the fundamental frequency F1 using only F1 and F2? Okay, the secret here is remembering that closed pipes are kind of picky. They only have odd harmonics. So if the first resonance is F1, the very next one, F2, can't be 2F1. It absolutely has to be 3F1. Once you know that, it's just simple algebra. We have the equation F2 equals 3F1. Now, let's subtract F1 from both sides. That gives us F2 minus F1 equals 2F1. Then, just divide by 2. And there's your answer. F1 equals the difference between F2 and F1, all divided by 2. And let's do one more, a calculation from NECO. This time, we have a closed pipe that's 33 centimeters long, and its main fundamental frequency is 250 Hz. Based on just that information, what's the velocity of sound in the air? And just like before, watch out for the units. They gave us the length in centimeters, so our very first step has to be to convert that to meters. After that, it's easy. We just take our formula for the fundamental frequency of a closed pipe, F equals V over 4L, rearrange it to solve for V, and plug in the values. And look at that, we get 330 meters per second, a very standard value for the speed of sound in air. So we can be confident in our answer. Whew, we've covered a lot of ground. Let's wrap this all up with a quick fire round of the most important formulas and some pro tips to make sure you walk into that exam hall feeling totally confident. Alright, let's put everything you need in one place. This slide has the 3 essential formulas you have to know: the period for a spring system and the fundamental frequencies for both closed and open pipes. Seriously, I'd pause the explainer right now and take a screenshot of this. It is the perfect summary for your revision notes. And please remember these simple but vital exam techniques. Units are free marks, so don't just throw them away. If you ever have to draw a diagram, label everything. Assume G is 10, unless they tell you otherwise. And always, always show your work. Because even if you mess up a calculation, you can still get marks for your method. So what you should really take away from all this is that the physics of vibration is not just some boring topic for exams. It is everywhere. The next time you see a skyscraper swaying in the wind, or you hear the sound from blowing over the top of a bottle, or even feel the rumble of a drum, I want you to think about the simple harmonic motion and the stationary waves that are making it all happen. Good luck with your studies. For more practice questions and solutions, visit examkp.com.